Welcome to The Explainer. Today, we're pulling back the curtain on the hidden rules that power our digital world. You know, the frameworks that make everything from sending an email to streaming a movie even possible. Let's just dive right in.
So, have you ever really thought about it? You type up a message, you hit send, and bam, it's on a screen halfway across the globe. It feels like total magic, right? But behind that one little click, there's this incredibly complex, super high-speed process kicking off.
Yeah, it's definitely not magic. It's this hidden, multi-step process that makes our whole digital world work. And that process, it's all governed by a set of rules, or let's call them models, that make sure every single device is speaking the same language. Today, we're going to dig into the two most important blueprints for the internet, the super detailed OSI model and the one we actually use, the TCP/IP model.
All right, first up, we've got the OSI model. Now, you should think of this as the ultimate conceptual guide, a really detailed 7-layer framework that breaks down every single step of network communication. And the genius of it is that each layer has just one specific job to do, and it only talks to the layer directly above or below it. This whole modular thing is key. It makes building and troubleshooting these incredibly complex networks so much easier.
So we're going to start at the very top, at layer 7. This is the application layer. And honestly, this is the only layer you actually see and interact with. It's your web browser, right? Your Gmail tab, your WhatsApp chat. It's the part where you're actually typing your message and telling the computer what you want it to do.
Okay, just underneath that, we've got the presentation layer. Think of this layer as the universal translator and security guard for all your data. It takes the info from the application and, well, it makes sure it's in a format that literally any other computer can understand. And often, it'll encrypt or compress it to make sure it travels safely and efficiently.
Next up is the session layer, and this one is basically the conversation manager. Its job is to open up the communication channel, keep it open for the entire time it's needed, like during a video call, and then it closes it all down once the conversation's over. It's all about managing that back and forth dialogue between devices.
All right, now we're getting to the transport layer. You can think of this one as our reliable delivery service. It takes your big message and chops it up into smaller, much more manageable pieces called segments. And its most crucial job is to make absolutely sure every single one of those segments arrives at the destination in the right order without anything getting lost or mixed up.
So, the network layer. This is basically the internet's postal service. This is where your data gets its address. The source and the destination IP addresses get stamped right on. This layer is responsible for all the routing, for figuring out the absolute best path for your data to take across this huge, complex web of networks. And if the network layer is the global postal service, then you can think of the data link layer as your local mail carrier. Its job is to handle getting the data from one specific device to the very next one in the chain, like say from your computer to your router. And it does this using those hardware-specific MAC addresses.
And finally, we hit rock bottom, the physical layer. This is where all that data becomes an actual physical signal. It's the raw ones and zeros traveling as electrical pulses through an Ethernet cable, or as pulses of light through a fiber optic line, or even as radio waves for your Wi-Fi. This is the physics that makes it all happen. Okay, so as your data travels down through all these layers, this process called encapsulation happens. Each layer basically wraps the data from the layer above it, adding its own little bit of information. Kind of like those nesting boxes you see. It just keeps getting put inside a slightly bigger box. And as it gets wrapped up in each of those new layers, the name we use for the data unit actually changes. See at the top, it's just called data. But then the transport layer calls its little pieces segments. The network layer calls them packets. The data link layer calls them frames. And then finally, it all becomes bits down at the physical layer. And hey, if you're trying to remember all 7 of those layers, here's a super handy mnemonic for you. Just think, all people seem to need data processing. That gives you application, presentation, session, transport, network, data link, and physical, right from top to bottom. Okay, so while that 7-layer OSI model is the perfect theoretical blueprint, it's not actually what the internet runs on day to day. For that, we turn to a much more streamlined, practical model. Which brings us to the TCP/IP model. This is the real workhorse of the modern internet. It basically takes all those core concepts we just learned from the OSI model and condenses them down into 4 practical layers that just, well, they get the job done efficiently. So the TCP/IP model kicks things off by bundling the top 3 OSI layers. That's application, presentation, and session, all into a single application layer. This one layer handles everything from the user interface to formatting the data and managing the whole communication dialogue. All right, the next layer down is an easy one. It's the transfer layer. And guess what? It does the exact same job as layer 4 in the OSI model. No changes here. It's still responsible for that reliable end-to-end delivery of data, making sure nothing gets lost. And it primarily uses the transmission control protocol, the TCP and TCP/IP to do it.
And it's a similar story for the internet layer. This one, in the TCP/IP model, maps directly to the network layer from the OSI model. This is where the internet protocol, the IP, lives. It's all about addressing and routing your packets to their final destination across the entire internet. And finally, the TCP/IP model combines the bottom two OSI layers, that's data link and physical, into one single layer called the network access layer. This layer handles all the hardware stuff. The network cards, the cables, the Wi-Fi signals, basically everything needed to physically get those bits from one place to another.
And we couldn't leave you without a mnemonic for this one, right? To remember the 4 layers of TCP/IP, just think all tigers in Nepal. Simple enough. That's application, transport, internet, and network access.
All right, so we've got this 7-layer theoretical model and then this 4-layer practical one. So let's take a second to look at exactly how they fit together, and more importantly, why we even need to know about both of them.
The best way to think about it is like this. The OSI model is the super detailed, perfect architectural drawing. It's fantastic for learning and for making sure everything is standardized, but the TCP/IP model, that's the actual building that was constructed from those plans. It's more practical, it's less rigid, and it's what the internet is literally built on. And this chart right here just perfectly illustrates that relationship. You can see exactly how those 7 OSI layers just kind of condense and map directly onto the 4 layers of TCP/IP. It really is the same core logic, it's just packaged in a much more practical way.
Okay, so at this point you might be wondering, this is all pretty interesting, but why should I actually care about these invisible frameworks? And that is a totally fair question.
Well, here's the thing. These models are the very reason our digital world works, period. They're the silent foundation that allows, say, a brand new iPhone to talk seamlessly with a 10-year-old server. They provide that common language, ensuring what we call interoperability. For engineers, they're a roadmap for creating new hardware. And for network technicians, they are an absolutely essential tool for troubleshooting. If your internet goes out, they can literally check layer by layer to pinpoint the problem.
Look, these models have served us incredibly well. They've powered decades of digital transformation, but they were designed for the internet of yesterday and today. And as our technology just keeps evolving with things like the Internet of Things, quantum computing, even space-based networks, it leaves us with a really fascinating question. What will the rulebook for the internet of tomorrow even look like?